Hello, this is Carbon Lab, Made of Airs podcast, where we talk about material science, climate change, and, in our first season, plastics, a super impactful material. And while I'm not a scientist myself, luckily I have someone with me who is, to help me deep dive into sciencey topics, namely Dr. Oliver Gould. Oliver has spent the last 15 years leading scientific research in polymer composites and sustainable materials as a group leader and head of department at a variety of research institutes. He has published over 35 scientific papers and patents in world-renowned journals such as Science, Nature Communications, PNAS, JACS, and ACS Nano on topics such as soft robotics, biomass functionalization, nanotechnology, and carbon removal. At Made of Air, Oliver leads the R&D department as head of research and innovation, which works to develop new sustainable materials that can help reduce atmospheric CO2 levels.
Thanks for the intro, Barnabas. It seems natural to do the same for you. So Barnabas Horvath is our brand and marketing manager here at Made of Air. He's an ex-journalist with countless articles, while in the last decade he's been working as a marketing professional, helping startups and established brands to tell their stories, but also to grow and enter new markets around the world. Most importantly for this podcast, he's a textbook nerd and a huge science enthusiast.
That sounds just about right, thanks Oliver, and with that, let's roll our intro. The reason we want to talk about plastics, first of all, because they are everywhere, so they are a very important topic also from the point of climate change. And also, Made of Air is pretty much in that space where we try to make plastics better for the environment and also for companies who use them. So we decided that this is going to be the first few episodes we talk about. And we will start with a basic explanation of what are polymers and where do they come from. And with that, Oliver, what is a polymer?
Maybe we should start with what is a plastic. Or the word plastic derives from the Greek plastikos, meaning capable of being shaped or molded. And that's really the core of it, is that a plastic is something that has one form where we can move it around, we can ply it, we can shape it into different things, and another form where it holds that shape. So at the core of plastics is this idea of phase change, that we're starting with this liquid material that can flow at some level, and then we're ending with something solid that has this defined shape. And that's it. Yeah.
That's a plastic.
And that's a plastic.
Thank you for being with us.
So, as you already jumped ahead to, it's impossible to discuss plastics without talking about polymers.
Yeah.
The two are inextricably linked. And polymer fundamentally means something that has a lot of repeating units. The idea is that we have this small subunit, this motif, if you will, and that it is repeated lots and lots of times to make this kind of string, sort of linear case. And what's fantastic about polymers is that they're extremely versatile materials, and they're very easy to make exhibit this phase change.
A phase change is basically you have it in one state, which is usually, or what we usually do at MOA is we have a lot of pellets, let's say, small little bits, and then it's stable in that form. Then we heat it up, it becomes fluid, and then you put it in a shape, it cools down, and it stays that way.
Yeah, exactly. So what you're describing is a thermoplastic.
Yeah.
And what thermoplastics do is as you heat them up, they have a phase change. In the case of most polymeric materials, they undergo a melting. So something that was previously crystalline and ordered becomes, and stiff and strong, becomes fluid as things can move over each other and things can flow. And you can exploit that phase change to mold different shapes. So you put it in this liquid form, quote unquote liquid, you pour it into a mold or you push it into a mold and then you cool it down and it solidifies. And that's just one example of the wonderful versatility of polymeric materials.
Okay, so we have plastics today, but how they came to be? Where do they come from?
It's a great question, which I'm very glad you've asked. So, as everything, it all comes from nature, right? Someone saw something in the natural world and was like, wow, that's cool. I'd like to do that, but control it.
What did they see?
bend it to my will. And in this case, they saw natural rubber. So we have this material that exists, is produced from trees, basically. And for hundreds of years, natural rubber existed and was used for all kinds of things. There's lots of very prominent examples of the Aztecs and other Mesoamericans, am I pronouncing that right? Mesoamericans?
I won't help you with that, sorry.
Anyway, have used stabilized rubber for things like balls and for things like making waterproof seals on their materials. And they've been doing this since 1600 BC. The material, or rubber as it was, has been around for a very long amount of time and it's been used by humanity for a very long amount of time.
We in Europe didn't have that, so we have to first discover.
Yeah, so in Europe, a scientist called Charles-Marie de Condamine, and I'm 100% sure I pronounced that wrong, presented to the Académie Royale des Sciences, again, I apologize for pronunciation, of France in 1736. And in 1751, there was a paper by Francois Fresneau.
A lot of French people here, just to make it hard.
Exactly, that described many of rubber's properties. And then the name rubber, which is also very interesting, came along in 1770 because an Englishman, Joseph Priestley, noticed that the material was extremely good for rubbing pencil marks off paper.
Ah, that's an eraser.
Yeah, exactly. So like he rubbed it on some paper, and the story is also fascinating. Apparently, he accidentally picked up a piece of rubber instead of a piece of bread. And historically, apparently, at the time, a piece of bread was used to rub out pencil marks. But he picked up this piece of rubber he had lying around and found that, like, wait a second, this is much better than that slice of bread.
I have this feeling in general in science that basically how science progresses is you either find something good in nature or you do something stupid and you realize that that mistake was very good. Like happy accident, as like
for sure.
Bob Ross style.
But it's like insane to me that the whole name, like the whole etymology of rubber hinges on this one guy who accidentally used it instead of bread to rub pencil off paper one day and was like, rubber. Look at it, like I got a rubber here. Like, isn't that the weirdest thing ever? But anyway, this all sort of culminated in 1839 when Charles Goodyear, who you might know from the tire, discovered that sulfur-based vulcanization converted natural rubbers into elastomers. And this really gave birth to the whole rubber industry, because it was the point where we could produce that sort of rubbery quality on an industrialized scale. Over the course of the next 100 years or so, or a couple of 100 years, rubber becomes used for a lot more things. So things like car tires, things like gaskets. But basically people are still using natural rubber and they're still deriving it from trees mostly, or from agricultural methods. World War I happens, right? And let's paint a picture. We're at the First World War. Material scarcity is a big deal. So people are running out of all kinds of things and all kinds of different materials that they previously relied on because supply chains are being cut. It's difficult to sort of distribute things. And some of these materials include things that are sort of naturally polymeric. So things like silk, things like ivory, things like natural rubber are all suddenly becoming scarce. And there's a sort of theme in chemistry in a lot of early synthetic work that people develop things when they need to replace other things, and specifically when they need to replace natural products with something that is cheaper, easier to scale, more industrially available.
Because for a very long time, if I understand correctly, we used basically only natural rubber ever since Mesoamericans.
Exactly, and that sort of heralded all the major conceptual advances with polymeric materials, is that basically an interesting part of the story is people started making them really before they started understanding them.
Yeah.
So for a long time, people were making these quote-unquote polymeric materials, but not really understanding how they worked or what they were. People were playing around with cellulose. That is another natural product that obviously is a major component of trees and lots of other types of biomass. And early work in sort of 1847, a bit before the wartime we're talking about, people started doing the nitration of cellulose, and that's reacting it with nitrogen to form what became known at the time as smokeless gunpowder, but then slightly further on became celluloid, which I'm sure lots of people have heard of. The beauty of celluloid was that you could use it to replace ivory. You could also spin it and produce something that was similar to silk. And all of that was fantastic for obviously saving a load of elephants, but also great at manufacturing new products like combs, toys, toothbrushes, things that couldn't previously be made. And one of those products included billiard balls, and there's some fun stories here. Because as you may or may not know, celluloid is quite flammable. And again, as a sort of very broad general statement, nitrogen or nitrated things are also generally quite flammable. And so people are now replacing ivory, and specifically replacing ivory in billiard balls, and they're replacing it with this quite flammable nitrocellulose celluloid material. And supposedly, and this is another good indication of how early materials science is really quite sketchy and dangerous. Supposedly they manufactured these celluloid billiard balls, and there are lots of stories about how people would do things like you'd be in your billiard room, you'd be, chomping on a few cigars with the gentry boys. I don't know what the historical descriptor is there. And supposedly people would go to put out their cigars often on the billiard balls because they're generally ivory, very temperature resistant, but celluloid not particularly temperature resistant and also highly flammable, and the billiard balls would explode. And there were all these stories of people exploding these billiard balls by accident by touching them with their cigars. There's also a huge amount of stories about people using celluloid as film, as you also might know, being a man of the arts yourself.
Also very common in old movies when you see the film is not ending but burning out, basically.
Exactly, and this...
As a special effect.
As a special effect, right? Fun fire.
Yeah.
But obviously huge amounts of cinemas burned down at this time because they were using this early polymeric material, nitrocellulose, that was extremely flammable.
Okay, so we had celluloid and flammable billiard balls.
Exactly. So we have artificial ivory, which is an early example. And then we had also some synthetic silk materials. But the real big breakthrough was the development of Bakelite at the beginning of the 20th century. So in 1907, Bakerland managed to control the polycondensation of phenol and formaldehyde in the presence of acid catalysts. This is all probably too much detail, and produce what is sort of broadly known as the first synthetic polymeric material. And why that discovery was important, or why that really skyrocketed, is that it happened at a very ideal time. And it was an ideal time because the development of electrical stuff was happening. So the electrification and the developments of electrical engineering at the beginning of the 20th century were really just starting to take root. But the real problem that they had was that there were not so many very good insulating materials that could make that safe. So if you imagine you have all these high voltage, super conductive wires everywhere, suddenly for the first time carrying voltage and current that's very lethal around all over the place, you need materials that can allow people to work with wires and work with electricity.
And people were very scared of electricity at the
100%.
beginning. There were campaigns and it could kill, especially if you run bare wires everywhere.
Super dangerous.
Very dumb idea.
So what was fantastic was that Bakelite came along and polymeric materials came along, and they're unbelievably good insulators. And they're also very easy to make in shapes that are convenient for making wires, which lots of other materials aren't. So suddenly, at the same time, you have polymers and electrical engineering and electrification massively developing rapidly in tandem. And it's almost fair to say that without polymeric materials, we wouldn't really have electricity in the same way, or our electrical infrastructure would be so staggeringly different because of our inability to really make that practically functioning.
Yeah, for the people who mostly know Bakelite as vinyl and recordings, who are probably born after landline phones, right?
Yeah.
Older phones, like rotary phones especially, they were all made of, or not, maybe not all made of Bakelite, but a lot of them. And it was really, even in my childhood, it was, my grandma had it, and it was Bakelite. So it was really everywhere. It wasn't just records.
What is really interesting to me is that sort of all of these advances are happening without, as we sort of mentioned, a sound conceptual basis by which to understand what the materials were and how they functioned and what their properties were.
These early scientists basically brute forced their way and came up with some stuff without really knowing what they're doing, which is a very common thing in science history in a very weird way.
Sure.
X-rays, one of them, and radioactive materials. Let's drink them because it's a good idea. No, it's not. So there were a lot of weird stuff. But then there was one guy who actually had the feeling that this might be something else that others thought, right?
Yeah, there's always lots of guys, but the main guy, the most interesting guy to me at least, is a guy named Hermann Staudinger, who's widely credited with the sort of origin of macromolecular chemistry, polymeric chemistry. Yeah. He has quite an interesting life in lots of ways. So he sort of started as a biologist and then sort of decided that wasn't so interesting and ended up in chemistry. And as we sort of mentioned before, he starts his career working on lots of synthetic materials during World War I. So he's making things like synthetic coffee, he's making some other synthetic analogues. And he was very sort of aware of the developments around synthetic ivory and some of those other early synthetic polymeric materials that were replacing silks and stuff like that. And he fundamentally challenged the idea at the time, or the ideas about what these materials were at the time. And those ideas were that these were sort of particles in a way. These were particles that weren't really joined together. And maybe we have to do a brief segue into bonding here to outline how bonding works.
I'm ready.
But there are lots of different types of interactions between atoms and materials. And what we need to fundamentally know to understand polymers is that there's this type called covalent chemical bonding.
The good one. That's all I know about it. The strong one.
I don't want to discriminate between bonds, but they're all good. But anyway, in covalent bonding, we have things that are really attached. So they're really sort of joined together in a way that other sort of more temporary ionic attractions aren't. And at the time, there was this idea that polymers were just particles joined by these temporary interactions and not covalent bonding, or not molecules covalently bonded to each other. And that's a bit of a spoiler there, but it's fine.
At the beginning you said that polymers or plastics are really, really long chains of atoms.
Yep.
And this is what you're saying again, right? If they have these covalent bondings, that means that they can be very long. Am I getting that right?
Exactly. Okay. But so the length of the chain isn't necessarily what was missing. So the idea was that they're more colloids, and that word also probably doesn't mean anything to you, but like
very blank eyes, I'm here.
But kind of like a load of balls in a ball pit.
Yeah.
And sometimes the balls sort of like each other a bit, but most of the time they don't really care.
Yeah.
And that was sort of the idea, was that they were colloids, or just like balls that were sort of had these temporary interactions. But not that they were these really big joined molecules, like in the same way that H2O is a molecule, but enormous, like a huge chain of these atoms joined together going on forever and ever. But Staudinger came along and posited that instead they were these single molecules. They were these single enormous chains of atoms joined together by these covalent bonds. And unfortunately for him, well, at the start, that was greeted by a huge amount of skepticism. So there's all these like really interesting examples of people who basically told him that he was full of shit and that was complete like falsehood. And like really big famous chemists, so people like Emil Fischer, who was really a huge deal with polypeptides and proteins, very similar sort of biopolymeric materials. And he said all kinds of things. So like people are telling him things like, and there's a quote that he refers to in his memoirs. He says, "Dear colleague," this was someone addressing Staudinger. He says, "Abandon your idea of large molecules. Organic molecules with molecular weights, that's very, very long chains, exceeding 5,000 do not exist. Purify your products, such as rubber, and they will crystallize and turn out to be low molecular weight compounds." So what this means is people are telling him basically that what he's seeing or what he believes is just a result of impurity, of like not really having processed your material enough. And that if you just processed it properly, you wouldn't see these things anymore. And like all of these scientists are telling him things like he should quit what he's working on, and that he should go back to more beautiful, quote unquote, fields of research and abandon such disgusting and ill-defined compounds such as rubber and synthetic polymers, which at the time, in view of their properties, were referred to as grease chemistry. which is just hilarious to me as well, that like there are like literally dirty words about like polymeric materials and working with polymeric materials, that people were telling him that you're doing something disgusting, and
it was not cool to be a Greek chemist.
100%. Apparently it was not cool.
Why is it so important to understand the molecular weight of polymers? So why was his work so important in our everyday life?
That's a great question. So, and like the answer is that the polymers and plastics are very powerful because of their versatility. Because of the huge range of things we can do with them, we can produce things that have all sorts of properties, that are insulating, are conductive, are highly pliable, are very elastic. And the reason that we have that level of versatility is because we understand what these materials are. Like, these two things have to evolve together. If we don't have a conceptual understanding of what they are, we lose our ability to influence and change what these materials can be. So while there were good early discoveries, our ability to really make the materials we want and make the materials that plastics became and polymeric materials became, were because of his conceptual understanding and contributions to polymerics. So just to go a bit more into what his discoveries actually were, in 1922, his paper on rubber hydrogenation, he described or coined the term macromolecules. And that's an extremely important and everywhere term, which basically means big molecules. So again, as we said, things like H2O, CO2, these are small molecules, but he's really responsible for the idea that you can make these ginormous chains, these enormous molecules, which was so at odds with the beliefs at the time. And lucky for him, that obviously eventually he was proved right, or his theories were given the credit they deserved. And in 1953, he was awarded the Nobel Prize for Chemistry. Thanks to his achievements and work on polymeric materials.
So he was proved right.
He was proved right.
And we learned how to make plastic properly.
And there's an interesting piece of text from when he won that Nobel Prize, when he was awarded the prize, which is that he was told, "It is no secret that for a long time many colleagues rejected your views, which some of them even regarded as abderitic. This was understandable perhaps. In the world of high polymers almost everything was new and untried. Long-standing established concepts had to be revised or new ones created. The development of macromolecular sciences does not present a picture of a peaceful idyll," which really there underpins the opposition he faced and how sort of turbulent and difficult those discoveries and convincing the world of those discoveries was.
Okay, so he's proved right. It's 1953, right, when he wins the Nobel Prize.
Yep, exactly.
And basically, as far as I know, but you know much more about this than I do, after this time, plastics really started, or polymers really started to take over the world.
So he comes up with these theories, and he's coined the term macromolecules in 1922. And then really, after that, things are really exploding. So the recognition for the Nobel Prize comes a bit later, but thanks to lots of his conceptual advances in the 1920s and the 1930s, there's just an explosion of different materials with things like polystyrene, polyvinyl chloride PVC, polyethylene, and all these materials that are so unbelievably ubiquitous in the modern world are sort of very much coming on the back of that huge conceptual advance by Staudinger. And then really, it just kind of explodes from there. So that conceptual advance and then the industrialization of those materials just keeps pushing and pushing, and people are starting to realize the extreme versatility of those materials and the wide range of different things they can make with it. Really in the 60s, we're seeing this explosion of plastics in mass manufacturing. We're seeing techniques like injection molding and others sort of come online. And all kinds of new product categories are basically being enabled by the ability to really cheaply produce shapes or shape materials with good properties.
And just to understand it better, before that we had to use, for a lot of stuff,
wood,
natural
glass,
resources, or like
wood, glass, metals, things like this were basically what everything was.
Yeah,
for better or for worse.
And I found some statistics about it, like until or in 1950 we produced 1.5 million tons of plastics. 2015 we produced 322 million tons. So that's like a ridiculous jump. And it started around the 50s, right? So much so that it started to seep into pop culture. And in the 60s, in one of our favorite movies, or your favorite movies,
yeah, I mean, I do want to say just one word to you, Barnabas.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
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 Yeah, obviously The Graduate. And I don't know, I think that The Graduate is a really good example of the sort of buzz around the commercialization and industrialization of plastics that existed in the 60s and the exponential, unbelievable growth associated with those materials at that time.
And basically the scene is about how to be successful going into the business of plastics.
Yeah, exactly.
Which 67, the movie, and it is quite spot on, I would say. It is spot on.
I would say timely.
Yeah. And now what we see is plastics really are everywhere around us, for the better and the worse at the same time, I guess. And this is what we would like to talk about in our next episode. Why are plastics so amazing? We touched upon that topic in this one. And also, why are they horrible?
Yes, exactly. And like what specifically interesting for me is how plastics reflect the best and worst of our material culture and how we as a society deal with materials and treat materials. And how important it is that we understand the repercussions of the materials that we use, how they're produced and what they are. And I'd really like to touch on that in the next episode.
Yeah. So thanks for being with us, and see you in the next episode where we will talk more about grease chemistry.
Yeah.
And it's gonna get more complicated, I guess.
For sure. Extremely complicated.